Good morning, everyone. Welcome to our OCP Tech Talks for our Time Appliances project. Elad and Ahmed have done an amazing job of curating content for you. But before they begin, let me do a few housekeeping things. First of all, my name is Archana Haylock. I am the Chief Community Officer for OCP. This call is being recorded, so if you are not speaking, we would really appreciate it if you were on mute. It helps us with the quality of the recording as well as keeps the disruptions to a minimum. Number two is that you can find the recording along with the chat transcript and the slide decks probably within the next day or so. On the OCP past events page. And we'll post all the links to get recordings for this as well as previous tech talks in the chat in a few minutes. As far as questions are concerned, please wait until the speaker is done with their presentation to ask questions. You can post them in the chat, and the chat transcript is also being made available because sometimes questions come in and we want to make sure that they are addressed. And so we will address all of the questions either in the chat or, if time permitting, after the speaker has completed their presentation. So with that, I'd like to turn it over to our wonderful volunteer leads, Elad and Ahmed.
Hi. Good morning. Thanks for joining. Thank you, Archana, for setting everything up for us so nicely. And we will start. So we are on the 2022 Tech Talks. We are TAP Time Appliance Project. The project is now active in its second year of operation. We are the OCP TAP group, an interest group that promotes and develops improvements of time synchronization or time sensitive applications in data centers. And for today, we have quite a packed list of sessions. They're going to be blitz sessions, about 20 minutes each one, covering the vertical and the horizontal aspects of time synchronization on this planet today. I'll give a quick overview of our speakers and their subjects before we go further to explain, to capture who are all the TAP volunteers, what is our vision, and the progress that we have made to this day. So first, we will have, after the OCP TAP volunteers will talk, we'll have Kevin Stanton from Intel, and Kevin will talk about the synchronization, time synchronization, when it comes to when it goes beyond the walls of the data center in wireless links and even local interfaces such as PCI. Such diversity of support of time synchronization with other appliances will increase the audience of, will get applications to reach a wider audience in the billions, and we're all looking forward to hear about that. We'll have a TAP founder, Dotan Levy from NVIDIA, who will give the state of the union of time synchronizations in data centers and also highlight what's coming next, what can we do with precise time and some immediate applications and some immediate call out for actions as we are proliferating more and more applications into a time synchronized data center. Julian St. James from Meta will talk about Time Drive M.2. It's a new time drive version, a new protocol for wireless synchronization using UWB and state-of-the-art timing ASICs, and it's actually very exciting to see that coming to life. Anand Ram, he's leading our TAP instrumentation and measurement workstream, and he will give the progress that the team has captured so far in test methodologies, in open source tools, and then in the collaboration forum that we established. After that, 10:20, Lasse Jensen from TimeBeat will talk about time as a service, discuss the different ways synchronization can be delivered as a service, pros and cons and challenges of the different approaches that that are available today. And then Demon Chowdhury from Trimble will talk about GNSS receivers and as they remain the most cost-effective solution for synchronization today. He will share about the GNSS constellations means to protect and have a rigid solution as the geopolitical situation is unclear these days. Ulis Fakumar will finish off with choices for 5G data center synchronization and how the overview of choices and reference clocks that are used across data centers. It's a very packed list and we are thankful to all the volunteers. Please stay tuned and let's kick it off. So TAP, what is it all about? We are the TAP group, the time special group into looking into development and improvements of time-sensitive applications in data centers. And we have, in our vision, we have applied essentially two main objectives. One would be that we will establish a knowledge sharing community where experts in our field will be able to share of their knowledge and their progress on related subjects, not necessarily only the workstream related activities. And here is just a glance of the talks that we are hosting every other Wednesday, which are open for the public, and they're getting a lot of attention and they resonate. And from these talks, it's also that we're getting a lot of the feedback as to what should we focus on and where should we put our energy when it comes to work streams into development and actual specification. So the first thing is about getting the right experts and having a fireside open conversations on related topics. The next thing is obviously more actionable, and that's for us to put in place, as much as we try, open specifications and reference designs for TAP, for time appliances. On this front, we are working with work streams, subgroups that comprise of our volunteers, and we have already progressed with 3 of our first work streams. The first one launched last year is the Open Time Server, where we have a full reference design on how to design grandmasters open time servers in a data center. They are using building blocks which are available in the open market, and for that purpose, we also Meta has also open sourced the design of the time card, the Gerber files, the tools. A lot of the tools that are required for installing the drivers and measurements for a time server. And another work stream is the data center PTP profile, which also has come to a submission. And that is our very own first TAP data center focused profile. And we expect the time server and more appliances to comply with it. And another work stream is a work stream led by a TAP volunteer, Gary from Sometime. Gary, please speak up the next slide.
Thanks, Elad. So the oscillator workstream was started because when people look at an oscillator datasheet, they don't exactly know how to predict the performance they'll see in a PTP network. So the idea was to create oscillator classes, each class matching a particular node and application use case in the data center, and then specify performance requirements for the class, as well as test methodologies, because oftentimes the test, how you perform the test, can influence the result. And on the next slide, if you go to the next slide, Alon. we give an example of what's already been published so far, which is a class G1 Grandmaster. And here you can see there's a lot of different specifications for this particular class for an open Grandmaster in a data center in a traditional data center environment. And each one of these requirements here is documented in the link shown here for the requirements document. And eventually, we're working on now detailing the test methodologies for each one of these requirements. So I encourage anybody that's interested in this work to go to the OCP TAP website and look at previous recordings. Every meeting that we have is recorded, and recordings are available for viewing by anyone. You don't have to register to view it. And if you're interested, please contact me and we'll set you up and put you on the meeting minutes list and invite you in to the meeting and you can contribute.
Thank you, Gary. I would add that the calls go on almost every week, and the information is available on the project wiki page. There's tons of links here pointing to that page. Please direct yourself to the right work stream. Thank you for your dedication, Gary.
Thanks.
And as to what's coming up, we'll have more insights as to how to leverage 1, 2, and 3 already today, and how that democratizes precision time in data centers already, how that revolution can already be converted into actual gains. And you'll hear more about it at the TONS session and the others. However, we are also very busy with 4, 5, and 6. Ahmed, would you like to?
Sure. Thank you. Yeah. So the precision time API is basically a standard on, like, we're trying to basically make a framework, a standard of framework for software, how we like provide the precision time in like toward the user land, or let's say from user land access like this precision time, let's say PHC and other peripherals that they can directly reflect the precision that the like, let's say PTP or what you name it is providing to a system. The other one is the PTP servo workstream, which is led by Alon Regev. And sorry, the previous one also, the precision time API, is led by Georgi Chalakov from NVIDIA. So going back to the PTP servo, which is led by Alon Regev from Keysight, is about like, let's say two folds. Like, one is the controls, how we want to do the controlling to, let's say, mitigate certain specific problems to data centers. And the second part of it is the monitoring. So we can, let's say, monitor in real time, let's say, things like error bounds or fidelity, or things like holdover. And the sixth one, which is you mentioned already, is led by Ram, is the instrumentation and measurement, which is about tools we can build, which is like, again, it's the bread and butter for Calnex. Tools that are open source that can be expanded, let's say a feature expanded on, let's say, the time card or things like that, where you don't necessarily need some high-end device. You just want to monitor things at scale. And again, if you need, let's say, more like precise, like, let's say, measurement on let's say certain things on the time aspects, then you can go for commercial solutions. That's what Calnex is giving. Let's go next slide. So at the same time, we thought, like, we want to put some of these ideas moving forward, like with TAP, such as security, integrity, and reliability. So any of these pieces, they can become a work stream on their own. For example, we want to standardize sync databases. Like, what do we really need for databases to become, let's say, taking advantage of precision time? The other one is like what are we doing really for VMs? How are we pushing the precision time to VMs? And this also includes like how we do things, let's say with user land in general. And also time aware network. We can say like time aware network appliances. Like in addition to boundary clock and transparent clocks, what can we do? Can we, let's say, manage the queues, like the QoS that uses, let's say, precision time, so let's say minimize the variance for latency on packets as they go through the network. Also, time sync in existing DC networks. So let's say, what are the existing implementations, and how are we, like, let's say, going to like coexist with if something exists and we want to basically add things to it. Like, for example, you have NTP, how we want to put PTP beside it. Or let's say if you're using unicast versus multicast and you want to have them coexist. Another one is the improved holdover NIC, which we don't want to be prescriptive, but if we want to be prescriptive, it is, let's say, one instance can be, you can measure the temperature of the oscillator of a NIC to watch how, let's say, or any other, perturbing factor for the NIC when it goes on holdover, and then build a model, like a more like a measured model, basically, from how the NIC is performing when connection is there, sync is available, and then when you lose the sync connection, you can continue basically going on temperature, or again, any other perturbing things. Again, there can be two folds. One is you do correction. Another one is you calculate the uncertainty in real time. Also, fault detection recovery, no need to explain more. And you have also precision time over PCIe, which I don't want to spoil it. This is our next talk. And also we have the open GNSS receiver, which this can be an ongoing effort of whether we really want to have the GNSS open source or not. And it can come with different benefits. Let's say we can look at different methods for fusing, let's say, different constellations and so on. Open Mac, also another one of these open-ended things with a lot of ambition. Let's say, can we make a open source like miniaturized atomic clock, let's say rubidium or anything? And what does that really mean? We don't know. Again, it's not, this is just a teaser. Let's think about it. Like, do we really need to go toward that or not? And the last one here is, last but not least, is how are we going to go, let's say, toward the end user, like on the end user's computer, let's say, with a peripherals, keyboard and mouse, let's say, being time-stamped precisely, or let's say, how can we do the precision time over Wi-Fi to get to the end user's computer? And this can be extremely beneficial when we're thinking about all these cloud like services and the end user that is part of that, let's say, all kinds of virtual worlds and things that are coming ahead. Next slide, please. Again, to dig more in details, like I picked two of them. So let's say, for example, the challenges in data center networks is like, for example, you have this multi-host NIC, and it comes with its own challenges, like noisy neighbors or pause messages where the buffer is telling the NIC, hey, hold on, like I don't want to spike the buffer, or asymmetry in round trips, or road changes. Like, again, these things are like driven, let's say, by BGP or other like algorithms that are already existing, established in data centers, and they're not supposed to consider the route for a sync packet. All the packets are treated the same. So now for these kinds of, let's say, existing algorithms, how can we leverage or improve the performance for sync? And we thought like a lot of these things may fall, let's say, on how servos are going to handle things and so on. Also, a balance between like the oscillator performance and the network fidelity is like more of a cost thing. Let's say you have millions or hundreds of thousands, or you name it, numbers of NICs. how much, let's say, cost you want to add into the performance of the local oscillator versus how much you want to invest on the network to provide that. And also the future of PTP compliant, compliant NICs, which I already mentioned. And also about the adoption for precision time all the way back to, let's say, all the way down to, let's say, the end user. And we thought like we can actually think about it in horizontal and vertical. Let's say horizontal is like you expand it to other data centers and all data center will be aware and so on. Versus you go down to user land and peripherals and so on. Okay, next slide, please. We have our friends from NetTime Logic. They're gonna update us with the latest effort on the open sourcing the time cards FPGA.
So, hello everyone. Yeah, here we would like to give you some update on how the project has been going on the FPGA of the time card. And yeah, we have some good news because the first open source version of the FPGA project has been released. If you would like, we could go to the next slide. So, short overview of the timeline of the project. Already by 2020, the first version of the time card FPGA binaries were available. That was not an open source design, but the binaries were could be used free of charge. And lately, the Git repository has been updated with a base system open source FPGA, where you can find the IP cores by NetTime Logic and also documentation for its core and the overall design and scripts to easily create the project, implement and generate the binaries. The next step of the project will be that in the following months, we will release an updated version where PPS and TOD slave, time of day slave, will be available. So then the FPGA can be synchronized fully by GNSS input without the need of software support. Feel free to check on the links, and there you can find the clear structure of the project, and hopefully the documentation can guide you on how to generate the project.
Thank you, Yannis. So in addition to this link that you see is shared here on the screen, Elad, can you point it with the laser? We have also a simplified one, just timingcard.com. It takes you straight there, and then you can basically reach out to all these things on the Git. So next slide, please. So next, we are introducing a new hardware, the TimeCard Duo. So TimeCard Duo has, I mean, there are a lot of changes. Mike will update us, but the very obvious one in front you can see is now you have 2 GNSS receivers. And with that, you can do a lot of interesting things. Mike?
Am I showing up?
Yes.
Hi all. So yeah, thanks, Ahmed. So released soon on GitHub. Obviously, the previous versions of the time card have been more prototypes, and we've converged to a time card that now we aim to support moving forward as a more stable version. What the goal of this was, the biggest addition was the second dual source for the GNSS. And what we're aiming to do with this is to establish these platforms, the size and the shape of the GNSS as an evaluation platform going forward, so that we can compare directly on the same time card performance of different GNSS modules and different internal algorithms that are running in our systems and research devices and research moving forward. The second thing that we also did, as you noticed, we swapped the position of the Mac and of the FPGA just to better suit mechanical performance and have the higher weight items in the center of mass. Another feature that we also did is we improved the signal integrity performance of the input and outputs for PPS in, out, 10 megahertz signals and other auxiliary signals that will be outputted there. And the final thing as well that we've also added is additional PPS in and PPS out for the Mac and additional auxiliary signals from the FPGA. Finally, one for debugging, we've added a modular PMOD connector to allow others to connect debugging devices or to connect additional sensors or other units that do not natively have support with the time card platform. So yeah, once again, available on timingcard.com. And previous versions won't necessarily be deprecated, but going forward, this will be the research platform for TimeCard and for testing and for further research.
Thank you very much, Mike. Also, in addition, we have another version which we thought like we will keep it for now, like because there's some still development on it. But that one basically will use the CSAC, the cesium version, and it will look pretty similar. Just the Mac is basically where the Mac is. You have a CSAC and you have less power consumption. Also, one more thing is you have two GNSS receivers, so you can have, let's say, a combination of L1, L2, and then L1, L5. In this case, like we have a L1, L2 on the left side. On the right side, we have a L1, L5. So the one left is from uBlocks, the one on the right is from Trimble. And the cool thing is you can watch both of them. The performance of both of them have like certain filtering or switching mechanism that can use, again, more insight on the fidelity of the signal, and then based on that can switch back and forth. So let's say you have spoofing or jamming or something, it has to be pretty comprehensive to shut down what's going on with a card. And it has to be more than days because the Mac is basically providing a lot of stability. That's it from my end.
Thank you, Ahmed. Thank you, Julian. Yeah, sorry. Thank you, Mike, as well. And just in time, we're going to move to Kevin Stanton from Intel, and I will give you this stop sharing and let you take control of the screen.
Okay, great. Thank you. So hopefully I can get the right screen. I think it's this one. Yes.
Yeah, we can see that.
And you see the full screen?
Yes, the floor is yours.
Excellent, thank you. All right, I'm Kevin Stanton. I'll be talking about time synchronization beyond Ethernet. And in particular, I'll start out with synchronization within the application, within compute systems to the software. So software access to now. I'll spend most of my time talking about that because it's a critical part of delivering time all the way to the place, the last inch where time is actually needed by application software. And then I'll also mention various other non-Ethernet methods of time synchronization, either between systems or within the system. So the problem statement is that I'm writing software and I want to access what time is it now, and I want that time to be accurate. I want that time to come from, for example, 1588 over the Ethernet or other network. The problem is that often what time it is because we need it to be accurate, is related to the silicon, the Ethernet silicon, and to go out and reach all the way down to the network interface and find out what time it is. That can take some time. It's very slow and increase a lot of inaccuracy. So the one approach is that you take the time from the local area network, the LAN driver, the LAN device, Ethernet NIC, and make a copy into the CPU. The problem is that, and then of course, there is very low latency to access the time. The problem is that that does not really scale. And I'll show you why in a second. Here's the next slide. So we in modern computer systems, we may have multiple applications. We may have multiple operating systems. We have multiple tenants. and multiple interfaces. And in some cases, we have multiple sources of time. Those could be, some of them could be traceable to TAI or atomic time. Some of them might be just local references. Some of them might be redundant copies of time. And we don't want to force all of the averaging, Kalman filter, whatever happens to bring these together. We don't want that to be forced to be in the NICs. We want to be able to apply software to that. And so another important thing to note is that modern CPUs have a counter which runs at the nominal max frequency of the CPU. These days, those are synchronized between all of the cores in a socket and even between multiple sockets. And so the question is, how can we use this counter to provide accurate time that's immediately available to any application running on the system? So the concept here, and I'll just briefly describe it, is if we have a CPU counter, for example, the timestamp counter, and if we could multiply and add by M and C to create an external timescale, maybe this is the PTP GM0, and here's a redundant copy, and maybe we have some NTP time as well, then we could use a single counter in the system, hardware counter, to create on demand these various representations of the external timescale. All you need is a multiply and add, and these days, those are pretty fast. The question is, how do you get the M and the C? And how do you actually access these various time scales and indicate which one you want? Well, just as an example, and we're not going to do a code review today, but in Linux, it implements POSIX clocks. And I can call clock get time and ask for the raw time, raw monotonic time, which is just the CPU counter scaled to nanoseconds. I can ask for the monotonic time, which is scaled to whatever the GM is synchronized to that I'm getting over the network. Or I can ask what time is it in actual wall clock time. And by the way, there are a number of other clocks being expanded so that we can represent multiple 1588 domains in the system at the same time. So that looks like this on the right, where we have a counter, which is just a free running counter. We can multiply by the nominal nanoseconds per tick. And then if we know the M and the C, which are going to be dependent on runtime. In fact, the M needs to be adjusted continuously because, as we were just talking about, oscillators will change in frequency based on temperature and so on. So the M is the critical piece that we need to measure. And then the C is just the offset compared to 1970. And then this can then create 1, 2, and 3, 1, 2, and 3 that we talked about. And it turns out that in Linux today, we have this PTP time to system offset call. And you can add on _precise. We'll talk about that in the next slide. And what that does is it goes down and it reads the network time. And then it reads one of these times, and it gives you the pair back, actually a triple. So that you can say when the network time was this, the local counter was that. And from that, you can create a linearity relationship. The point is, all of this is part of Linux today. It works great, but the challenge has always been this: how do I access what time is it now out at the NIC? So introducing now precision time measurement over PCI Express. So this is part of PCI, and it allows the system time to be propagated over a PCI switch, in fact, over to a NIC device, for example, in a similar way to the way 1588 propagates time from a GPS system, for example, to all of the devices that need to know what time it is. So at the end of this protocol defined by the PCI SIG, you can end up with this pair, which is very, very accurate, single-digit nanoseconds accurate, that has the system time and the PTP time both captured together in hardware on demand, which can then be provided up to that call with the _precise appended. And then this gives you a very accurate means of computing the M, so that you don't need to worry about reaching all the way down into the NIC to find out what time it is right now. You have an accurate M, you ask what time it is, it reads the CPU time, which is very fast, it does a multiply, add, and there you go. Okay, so this is within, let's call the last inch of providing time to software. And then I just wanted to mention also some non-Ethernet time synchronization methods. And but before I do that, I just wanted to back up just for a second and say that the OCP TAP, I want to commend the team, the organizers, all the contributors. Yes, there's a regular call where people talk about time synchronization, use cases, and so on. And those presentations are made publicly available, which is great to spread all of the knowledge and all of the things that people are experimenting with. But OCP TAP also builds things, and I think that's really important to get our hands dirty, figure out stuff, build actual hardware upstream into Linux, make it available to the community. I think it's a huge service, and rather than just talk about this, taking action and building is really important. Okay, this is my last slide, so I'll just walk through this to talk about other non-Ethernet methods of time synchronization. So with Ethernet, that's pretty much the focus of much of the effort today, and it's not a surprise because data centers are Ethernet heavy for sure. We talked about PCIe PTM, which allows us to get synchronization from a network interface to the application software in hardware with really, really good accuracy. I didn't mention it on the previous slide, but when I talked about PTM, Chris Hall has given a presentation to OCP TAP that you guys can go back and watch on YouTube, and he shows measurement methodology as well as some performance measurement. They're very impressive. It's a surprise to a lot of people that USB also defined a precision time measurement method, where the USB bus clock is used as a shared reference between the host controller and the device, the USB device. And silicon support, though, in the devices is lagging today. So if anybody has need to provide accurate time to a USB device and you have some influence on the silicon that is built there, there is a specification, and host controllers are actually required to support USB PTM. So that part of the link is supported today in the silicon. And then really as part of time-sensitive networking, which is not so relevant to OCP TAP, but a place where time synchronization is also very important for automotive, industrial, manufacturing, energy, even AV, live AV distribution, time-sensitive networking, which defines a profile of 1588, just like OCP TAP defines a profile of 1588. That expands time synchronization beyond Ethernet to Wi-Fi, and in particular, the timing measurement or fine timing measurement protocol is actually a protocol defined by 802.11. It's very similar to a P-delay four-way exchange that 1588 defines. And because it's defined below, well, within the Wi-Fi MAC, it's actually immune to retransmission. So if there's a retransmission over Wi-Fi, you capture the timestamps again, and you're not experiencing the jitter of Wi-Fi because you're inside of the MAC and you can get these round trip delays measured very accurately. And you're limited only by the multipath of the wireless channel, which should be in the foot per nanosecond kind of range. So whatever the multipath would be. So, and if you're interested in looking in finding out more, there's Avenue Alliance is a group that has a white paper that actually describes Wi-Fi time-sensitive network as well as 5G time-sensitive networking, which includes time synchronization as a fundamental part. Finally, 5G URLLC, that's ultra reliable, low latency communication. Everybody hears about 5G. It has three different modes, let's say. One is very high bandwidth, one is very low power, and the other one is ultra reliable, low latency communication. And 5G URLLC in the 3GPP defines a mapping over of 802.1as and the rest of time-sensitive networking over the whole 5G system as though it were a switch. So Ethernet comes into the 5G system, 802.1as, the 1588 profile runs, and then you have a wireless link to the UE, and that they share a 5G clock internally to the 5G system, and then it's remapped back to PTP semantics on the outside, and you can even then go back to Ethernet with a 5G looking like a very complex switch with Ethernet in, Ethernet out, synchronization end to end, which is really important to have the end to end from a GM all the way from to Ethernet to 5G back to Ethernet, maybe to Wi-Fi, and then to sensors and actuators from some IoT applications. There's another Google search you could do that would pull that up. And then ultra wideband, I think Julian's going to be talking about some applications of time sync over UWB. I3C for sensors has a time synchronization methodology to get time out of the MEMS sensors, for example. GNSS is spoken about. And if you care to put an antenna on and listen to a broadcast from Colorado in the US, for example, you get WWV for your time synchronization. So synchronization outside of Ethernet, it's a rich ecosystem. A lot is being done. And as we talk about getting synchronization within the data center and then outside of the data center all the way to the devices and the users, some of these will become important. So thanks.
Thank you, Kevin. I wanted to point out there, we have on our website a previous session by Kevin. I just put the link here in the chat, and another one, Kevin's colleague, Christopher, on timing in the last inch. So these are good sessions for reference to always go back to. Are there any questions? I didn't see people raise their hands. Thank you. All right. Our next speaker is Dotan Levy. He founded with us TAP some time ago, and he is leading the research and development team for timing in NVIDIA. Dotan, over to you.
Hi, everyone. Good morning. I'm going to share my screen. Do you see my screen?
Yes, we can.
Okay, so this talk will focus mostly on the data center, which is for many of us still the bread, butter, and home for compute and for all the visions and dreams that we have. And in the next 20 minutes, I would like to share with you a bit of the status that we reached. I know Elad and Ahmed talked about it a little bit. I plan to unveil a bit more. And I want to discuss the next three major challenges that we believe we are facing in order to make the next leap, and what you, each and every one of you can do to participate, to join, to help. So as I said, I'm gonna give a bit of an overview what has been successful since TAP being established. Actually, there is quite a big impact. And then the next three challenges, as I see it, I need to put this disclaimer, of course, which the first one is, how do we extend and improve the service some of top work stream touch on those things. We must achieve a reliable clock. I will explain why and what that really is, a reliable clock. And we still start for a better accuracy. The second one is to find and explore, research more time sync use cases, more application that time synchronization could be beneficial, could make the difference. Since we know that we vandalize this time service in a data center, it's pretty obvious that almost any application never thought about the option to leverage this service. So I will share with you a bit of what we achieved so far in those use cases, and and maybe it will enlighten some of you to explore more or a different application that could leverage this. And my last challenge, which I think is very important, as you see, Gary is leading an oscillator workstream. This oscillator workstream was mostly established because those clocking device, oscillators and all this family of devices, not just oscillator, were not defined for a data center. So the first thing that Gary is handling is the data sheet. How do we find and fit the best oscillator for our use cases? And Gary actually translating everything into data center language, assuming data center environment, etc. And this is, of course, the first thing that we should have done from our point of view, and that's what we did. And I really appreciate what Gary is doing. But it's not the end. As we move on and we take those clocking devices from vendors that doing amazing job synchronizing clocks, disciplining all those analog devices, sometimes even digital and mechanical devices, and we bring them into the data center. That brings us new challenges, and I'm going to talk about it because this is another transformation that we need to do to the market in order to make it happen. And everything will be accompanied with a call for action. TAP is not TAP. OCP is all about collaboration. Everyone here is not just a listener. We invite everyone to contribute, to share their wisdom, their thoughts, their dreams, and sometimes their time, of course. And I will tell you, if you want, what we think you can do. So I think that by far the most biggest thing that was achieved by TAP is that scaling up the PTP service. I mean, before this project, we didn't know about any large deployment as we have today. In Meta now, deploying the PTP service, relying on TAP capabilities and TAP product and TAP standards, and that's an amazing thing. And we do see that future looking, it will be spread across more and more cloud providers and hyperscalers. The second thing I think that we made is we discussed it in the and we presented very nicely in the conference that we had last November. The fact that we managed to scale up Grandmaster node to sync millions of nodes. I mean, there were a few debates how to go and how to make this transformation, how to scale up. The naive PTP approach would be to expand the tree. So you have boundaries of clocks, and the tree goes deeper and deeper and deeper, but that evolve and introduce a new set of problems that we had challenged to overcome. And sometimes there is a saying that I like, quote, you don't know that something is impossible, so you just do it. It appears that there was an assumption that it's not doable to sync such amount of ordinary clocks using one grandmaster node. And my friends here at Meta did an amazing job bringing this frontier. Of course, as a hardware vendor, we supported everything, but it's fully their achievement. And they even open up everything so you can copycat this amazing Guinness record, I would say, by far. Actually, I think they broke the Guinness record 3 times during the development. And that led to the largest PTP deployment known with a 0 boundary clocks, which is an amazing thing. And in case you missed what is so good about that, that means that each node can measure its own offset from the grandmaster, which is something you cannot do easily when you have boundary clocks. And as we will discuss further, you will see how important it is in data center. Then the operational thing. I mean, once we came up with the technology, the Meta guys came up with all the challenges that they must overcome in order to make it operational, to run it in a script, to tear it up, to tear it down, to monitor it, etc. I think that most of it hasn't been exposed yet. I think we will expose it more and more. Those things are still evolving, but this is a major achievement. And I think the most impacting one on the financial thing is that we saved a lot of money. I mean, this acceleration thing, the fact that we managed to accelerate a huge distributed application using TimeSync, that save money, save power. So you can see it as a green project. You can see it as a cutting edge technology. In every vector that you see, it's groundbreaking. So let's talk about what's next. I mean, of course the journey hasn't finished. You see, I guess you saw Ahmed's slide on what's next. The list is much more bigger than 3, but I think those 3 challenges, if we overcome them in the next year, will have a major impact. So the first, as I said, is to extend the service. We need a reliable clock. I will explain why and how. Leveraging more application, which means taking this technology to more and more use cases, to more and more places where we can save money and accelerate. And then the vendor thing, the component thing, how to use the components that the market now has into a data center, which is a non-trivial market. So let's start with first. Why do we need a reliable clock? There is a paper that I'm happily sharing here the link. I learned a lot from this paper, and I would like to thank Google that joined for some time and contribute some of their knowledge. This paper describes what happens if the clock is non-reliable. Actually, I think it's easy to explain. When you take and use the timestamp as your guarantee for orderness, and you rely on your timestamp instead of mutexes and semaphore, that on one hand, it brings you this amazing acceleration that we get. But on the other hand, if for some reason the timestamp is wrong, it leads almost immediately to a silent data corruption. That means that the data is corrupted and you don't know. And this is probably one of the biggest catastrophe that distributed app or cloud application could have. Now, in order to avoid that, this is a work that already been done. The Google team developed a true time API, which is an API that determines every time that application asks what is the time, it gets 2 times. It gets what is the time now and what is the error bound. Maybe the semantic is like this, but maybe the interface is a little bit different. Nevertheless, application gets not just the time, but a bit how inaccurate it is. And what we want to do, of course, first of all, we want to state that the problem statement is very clear and highly accepted by us. we truly agree with that problem statement completely. But we a bit disagreeing about the solution that was described in the paper. We think it's not scalable enough, and it's a huge burden to deploy it. And we are now exploring a few different things. So what we are exploring, and again, TAP is all about collaboration. If you want to change what we explore, if you want to add another exploration path, you are welcome to join. So the first thing that we did already is we established a work stream on clock interface led by our almighty Georgi. And they're doing an excellent job, and he is not presenting because the work is not done yet, so it's not finalized. But Georgi's task is to extend the clock interface to include parameters and internal know-how from the clock hardware that will eventually allow the software to calculate by itself the error bound, even dynamically and not statically, which means that we want to expose everything that you need in order to calculate by your own algorithm, your error bound. Take your own margin, take your own risks and trade-off between accuracy and reliability. As well as the confidence level, it seems that some hardware, there is some hardware know-how that we can expose in order to allow software to understand if there is more certainty or uncertainty in that specific timestamp. And the first call for action on this topic is join us, at least come as a listeners and learn. There is a lot to learn. Everything here is new and quite innovative. And we are looking for more brains to brainstorm and more challenges to solve and more people to collaborate. But we also wish to explore a more reliable service, which means that we want that the clocks will not be synchronized only one per sync interval, which in PTP is at the moment it's millisecond. We want to add some more reliability with that, and we are thinking in a data-centric way, which means that we think in a scalable way. So the approaches that raised so far, but we haven't done anything yet in TAP on that. It's just like the brainstorm, and I think we will establish a work stream soon if people will join. One option is to use big data. I think Las will show you what you can leverage when you use big data. Las as a great session here today. Las from TimeBit. So this is one direction. The second direction is to use physical layer assistance, similar to what the telco is doing, but we will try to take it into a data center direction. And maybe we will extend PTP protocol to allow such things. So that was on the reliable clock, which is a must to leverage those applications. Now I want to show you some of the success stories that we have. As far as I can, those are private success stories, but I can tell you a bit on each and every one of them. So TimeSync is used successfully to synchronize globally distributed databases, and the published number is 3x acceleration, which is a very compelling number. That was the first success. There were papers describing how to do that, and TAP made it happen. TAP and Meta, of course. Then timing as a service. I mean, public clouds runs VMs and they don't know anything about what they do, but offering time as a service to a VM. And then again, this is again related to the session that Las will have here today. That will allow cloud application to run time-sensitive application like e-commerce, FSI, etc. And this is a great achievement. And for those of you who still part of the engineering team, in the data center where everything is now distributed, there is almost no interesting workload that is done on a single node. It's very complicated to debug a huge cluster when something bad happened, to find out what was uncorrelated, how to correlate the event on one node to the other node, to a network phenomena, etc. But the fact that all nodes are synchronized, and the fact that the NICs and the infrastructure allow you to trace events on a coherent time axis dramatically aids the debug. We will publish soon something within NVIDIA on that topic on our own debug tools. And I think this is a major leap ahead. Now, it's not the end. 5G and edge. So some of you think about 5G as a telco thing. 5G is not just a telco thing. 5G is a technology. And we wish to connect it to our world to make a 5G node to look like any other data center node. And the key to do that, the first key that enable us to do that, is to have a very strict time synchronization. The last mile in 5G network is the frontal, and this is a TDM network. And this TDM network is very strict, and those timing capabilities are a must. And actually, this is one of the Lego blocks that allow NVIDIA, at least, to softwareize the entire edge of the 5G and to run, successfully run AI workloads, machine learning workloads. The entire CUDA ecosystem can run on data that came from the 5G. This is a major thing. It will be a major leap onwards, because a lot of the data that exists on the last mile 5G cannot even reach to the data center. So it's data that we could not process before. You can think of applications like smart cities, like traffic monitoring, etc. There are plenty, I mean, even industrial manufacturing control. The middle one talks about HPC. I didn't get an approval to disclose everything. I can say that we see some good success when we convert the HPC libraries that will allow us to leverage the collective offloads by using timesync. The idea is to load balance the inner networking, the east-west traffic, and not send everything at once. And then like avoid congestion with planning in a way. And we will publish on that soon, but it looks very promising. Even if we will hit 50% of our target, it's still a major leap. So stay tuned. And another thing is the services that run on enterprise. We know that's what we know, but there are probably some that we don't know. Broadcasting. I don't know if you know this, but the entire broadcast industry moved to Ethernet in order to allow 4K and 8K raw video streaming, media and entertainment, video walls, healthcare, synchronize the events on sensors, and the last but not least, the metaverse, omniverse, new thing that simulates everything in a 3D environment. And this is actually a key thing to make a success. And again, we don't know on all use cases. You are more than welcome. Actually, we very much encourage you to come and share if you know about more use cases or you have a question on the existing one. Okay, so the third one is what I call a vendor wake-up call. I want to share with you a lesson that we learned through this journey. What we did, of course, we now creating network adapters that has the capability to time sync, and we learned that we need a bit more. DC is a different market. DC is all about reliability, serviceability, and controllability. You know, those huge fleets are handled by an automation script, and that leads to some crazy phenomena. So first thing is the supply chain issue that the entire world is suffer from, but actually the data center was there before. Data center were always built from a supply chain reliability point of view. There was never a major component in a data center that was deployed in scale without an alternate source. And that, I don't know, some people think it as a competition. It's not, it's an enabler, okay? Without that, there is no way to deploy in such scale. So what we need to do, as I see it, we need to define those clocking devices, those analog devices that we want to deploy in the data center, and we need to make them standard in the way that they connect to the board, so we could replace one with another, and we could deploy them without any fear in huge volumes. So we need to create some language of pinout compatibility, and we need the vendors to do that. We started with that. We need the vendors to align up on this so-called pinout standard, and that's a major thing. We see it as a critical thing. Another point that I can make, but definitely those are just two examples, is fail-safe programming. As I said, in a data center, things are done in a huge scale. Like one button could start a chain of software upgrade for hundreds of thousands of nodes. Now, some of the procedure may include EEPROM burning or a new version and so on. And at the moment, because those devices are designed for a different market, they don't have a fail-safe operation, which means that if the power was shut down or something bad happened during this upgrade, then you are lost. Now, in the data center, it is a well-known method and practice that you have a fail-safe mechanism, you have a backup, and you don't switch the pointer on your boot image unless you authenticate it and make sure it's run. And we need this as well for those clocking devices. That's it. So just to summarize, encourage you guys to join up. I think you can understand we are doing here amazing thing. You can come as a listener, you can come to hear the great knowledge that we share, you can come and contribute. For you application architect, leverage this, okay? It's a new thing. Don't expect don't say that if it was a beneficial, someone would have done it. It's new, okay? And we intend to publish some kind of a cookbook soon. NVIDIA, I'm talking about here. We will publish some kind of a cookbook how to explore if your application could be accelerated. We have some tips and tricks. And for component vendors, reach out to find how to add robustness feature for your component. We are willing to educate you about what is needed in your portfolio. And come and help us establish that future workstream that we will declare. Thank you.
Thank you very much, Datan. We're going to switch presenters now. Up next is Julian from Meta.
Yeah, let me share my screen.
So welcome, Julian. It's been devoted to our project, and over to you.
All right, thanks a lot. So hi, everyone. So I'm presenting today about a hardware platform that I've been developing called Time Drive, and it's based around a UWB method for wireless synchronization. So the main problem that we're trying to address with Time Drive is how to get synchronization over these last few feet. So if you're in your house, or even if you're in a data center location where you're air gapped from a GPS antenna, how do you want to synchronize devices that don't have access to a traditional Ethernet network or that need other kind of infrastructure that's not available? So typical synchronization using a time card requires a GPS antenna connection, which is feasible for some locations, but not others. And also, even if it's feasible in the location, it might not be convenient for the device that you're trying to synchronize. So if I'm trying to synchronize even in my house, I might be able to put a GPS antenna near a window, but I can't necessarily run the cable all the way to the device that I'm trying to synchronize. Wi-Fi, like Kevin mentioned, it does have a capability for synchronization added in 802.11 AZ, but this is targeting a lower level of precision than UWB. So Time Drive is trying to explore what level of precision you can get with different wireless synchronization methods, namely UWB. I'll go a little bit more into UWB in a second. And then Time Card, the current solution that we have for synchronization of endpoints, also requires a PCIe slot and a atomic clock, which is quite large and not quite user friendly. So one of the other goals for Time Drive was to explore a small form factor, namely M.2, and see what we can do in an M.2 form factor to meet similar kind of utility that we get out of the time card. So why are we looking at UWB? So UWB is specified in 802.15.4. And the reason we're looking at UWB is because it's more designed for timing than Wi-Fi. So Wi-Fi has, its main design is for data communication. So in a spectrum, the frequency spectrum used for communication, it's not targeting a very wide frequency range. So it's trying to interact with other channels nearby. If you see on your Wi-Fi router, you select the Wi-Fi channels, they're not multiple gigahertz apart from each other. So it's more targeted for parallel residence of different channels, whereas UWB is based around using a very wide frequency spectrum. And the benefit of this is that it lets us get really sharp edges on any of the data communication that you do, which allows very precise timestamping of packet reception and transmission. So you're able to see us more like a square wave than you would with Wi-Fi, and also more than you probably would get with other Ethernet connections. So a traditional UWB application is based around precision location. So typically UWB is used for trying to find where you are in relation to another device. So distance between two devices. And how this works is that each device runs a counter running at 64 gigahertz. So each tick is approximately 15 picoseconds. So every packet that's sent or received, same as PTP, is timestamped against this counter instead of a 125 megahertz counter like PTP. So the range is computed just using time of flight, same as we do in PTP, but this one is using just direct speed of light since it's through the air. Accuracy can degrade with multiple things. So response time obviously makes a difference because your local oscillator is changing over time. So if you take too long to respond, your frequency drift might impact that at that resolution in the picosecond range. And mainly clock variation will affect this kind of accuracy that you're trying to get out of UWB. So I put some pictures here. These are the basic protocols that are used by a lot of positioning devices. So there's like a poll and a response and final, similar to PTP. So for commercial UWB, the most ubiquitous items are the AirTags or Samsung smart tags. So if you've ever used them before, you use your phone and it'll point to where the AirTag is and how far away it is. So the distance is computed using UWB, and they're able to get centimeter level accuracy using UWB range finding. And then to get the angle, they're using power sensitivity measurements of Bluetooth and other devices. For the smart tag, it's the same idea. So basically both newer iPhones and newer Samsung devices have a UWB transceiver inside of them. and they're using that to do range finding with the AirTags. It's designed for low power and also for very high precision range finding. But since we're interested in timing, basically distance is time in this case. So rather than using UWB to just look at times to compute the distance to a device, I'm using times to synchronize the two endpoints. So how would this work in a deployment? Let's say if Time Drive was a mature device, the vision is that we have Time Drive as a device inside of your, say, laptop or PC or even the Wi-Fi router. And then it synchronizes to a device that you put somewhere that has GPS reception. So you have a device that's broadcasting time basically from GPS over UWB. And then everybody else that is connected over UWB is able to get GPS time. So rather than needing a large GPS infrastructure or distribution network, you have one device that you can put wherever is convenient and has GPS, good reception. And then all the other devices are able to synchronize to a high level of precision over UWB. So either this could be a standalone device or in a Wi-Fi router. There are different schemes that could work, but this is the end vision of what we'd like to see at some point. So what is Time Drive? So Time Drive is an M.2 device. So this is a CAD model of it. And I don't know if it'll show up in the, yeah. So this is what M.2, what the Time Drive looks like in person. So it has a couple different chips. This is not based around an FPGA. So I designed it using a bunch of different discrete chips that have different functions. One of them is the Intel NIC, which acts as the PCIe endpoint. So you'll be able to do synchronization to the NIC PHC, same as you can with the time card. The only UWB chipset that I could find that would support this kind of synchronization scheme was the Decawave DW1000, which is a pretty common hobbyist UWB chip. For the main PHC, if you will, or timing control device, the analog devices 809546 is what I chose because it has some pretty advanced time stamping and control features, which I'll go into in a later slide. And then there's a simple microcontroller I kind of chose arbitrarily. And then I also put an OCXO, which you can't see in this block, but it's there. So for a compact M.2 form factor, we can't put a massive atomic clock. So I put a SI time OCXO for long-term stability. And the hardware design is currently on the GitHub. So this is all designed in Altium. And I also have some software up there. I'm currently developing it even now. So the one that I just showed was a Rev 2. The one on the GitHub is a Rev 1, but I'll be posting the Rev 2 design files pretty soon once I get it working. So there'll be more coming soon. And please contact me or anybody related to Time Drive if you're interested in development or testing. So kind of the theory of operation is that you have your I225, which acts as kind of your interface over PCIe, and then it has its PPS input disciplined by the DPLL. And then the DPLL's frequency and phase is adjusted by the microcontroller to align the Decawave over UWB. So similar like PTP, you are talking to a remote device and you're asking it what is, like sync and follow-ups and delay requests. And then you're computing your local frequency and phase offset. And then you're adjusting that frequency and phase offset in the DPLL, which is then fed into the I225 to discipline the PHC of the I225. So then you're able to get that timing, that time counter over PCIe as well. And it also has a few inputs. It has 4 timestamp inputs. So the DPLL can take multiple timestamp inputs, and it has 2 PPS outputs also. And they're using a very small coax connector that you can get an adapter to SMA. So the main reason that I chose this path for a Time Drive is that I wanted to explore some new features. So if we had gone with a an FPGA design, right now we don't have a PTM implementation for that. So I wanted to use the I225 to get PTM enabled on this device. So as Kevin talked about, PTM is how you get synchronization over the PCIe bus. So with this, the time drive will be able to get a higher level of system clock precision than you can even with the time card. So time card will definitely have better long-term stability and GPS connection, but time drive will ultimately have better PCIe synchronization capability because of this. So that's why I went with the I225 as my main PCIe bridge. And then for the analog devices, DPLL, so this is also kind of mimicking a lot of features we have on the time card. So the time card can support PPS output, PPS input, timestamping inputs. So the analog devices DPLL can do all these similar things, but with a higher level of precision. So it internally has 8 TDCs that it can use, and I'm using 4 internally on the card. And then I expose 4 on the time drive. So in theory, with the time drive in an M.2 form factor, you'd be able to timestamp 4 external signals, 1 PPS or anything, same as you can with the time card. So same feature in a much smaller form factor. But the timestamping is much better on the time drive because of the precision in the DPLL. So timestamping in the FPGAs is done with the internal logic. So it's limited by the frequency of the FPGA logic, which is typically 125 or 200 megahertz. So you have in the nanosecond level of precision. But the DPLL has TDCs that are able to give you picosecond level accuracy of the timestamping. And they have that characterized for each different pin that enables timestamping. So I put some datasheet pictures here showing what you can do on the DPLL. And so the ultimate goal for the time drive is to be able to make these high level timestamping measurements same as you can with a time card. And then also for the instrumentation work stream, the goal would be to have multiple time drives in a single device, giving you more PPS measurement capability than you can with any current instrument. So that's all I have about the time drive design. So as I pointed out, I'm currently working on the V2 and all of the major hardware functions are currently working. So UWB transmission between 2 time drives is working and I'm able to adjust the DPLL frequency and phase. So I'm currently working through the software development for the time drive to enable all these features that I hope to eventually expose. So if you have any questions, feel free to reach out to me or ask in the chat. And then I'll also be posting pretty soon the V2 hardware along with some of the Arduino sketches that I'm using to develop for it. And with that, I'll pass it back to Alad. Thank you.
Thanks, Julian. Let's see if we have any questions. There are a few minutes left before we move on. So feel free to go out of mute or raise your hand.
I raised my hand. Can you see it?
Yes, Lasse.
Okay. Okay, I was just wondering what distribution, okay, so between the 2 UWB devices, what distribution of offsets do you see?
What do you mean by a distribution of offsets?
I mean, how stable is the time transfer?
So that's currently what I'm developing. So, and also the boards I have don't have the OCXO on them. So I'm mainly just working on the software at this point. So once I get the algorithm stable, I'll add the OCXO for the long-term stability compensation and then do those kind of measurements. So what kind of offset you get between the 2 devices, and then also how aligned are they, both in frequency and offset.
So okay, so currently the offsets that you measure between the 2 devices, are they in the nanoseconds, are they in the microseconds? What do you currently see? The instant offsets.
Yeah, the goal, I'm still working on the disciplining algorithm, so I don't have measurement data just yet, but the goal is to get it into the nanosecond range. Yeah.
Lasse, may I jump in? So Lasse, the answer is stay tuned. We're very close to get the results, but as a rule of thumb, when you look at UWB, the precision is within, let's say, 3-4 centimeters. So use speed of light, and that tells you the uncertainty of time. So it should be somewhere, let's say, under 10 nanosecond. We'll see, however, like what comes. That's the theory. We'll see what comes from reality.
Yeah, I mean, 3 centimeters is what is like 100 picoseconds. You know?
Yeah, but I mean, the theory and reality, are
Yeah.
different things. We're changing really the purpose of the UWB. We're making it now. Okay, assume your position is stable. Give me the time. So that's the cool part about it. But stay tuned. We will share. I can assure you, you will find out before anyone else.
Okay, for what it's worth, Julian, I think it's very cool, and I'm a big fan, and I will follow.
Thank you.
Another question that was raised, whether the slides and the videos will be available, then the answer is yes. Go to our wiki page and find the Tech Talks link. Everything will be there. All right, thank you, Julian. And our next speaker is going to be Anand Ram, VP of Business Development for Calnex. Anand, over to you.
Great, thank you, Elad. Hello, everyone. Good to connect again and give you this presentation on one of the work streams that we have running at the TAP, at the OCP. So the TAP project, as you will have heard, has got multiple work streams that looks at different areas of technology or aspects of timing in the data center community. And the one that I'm going to talk about is instrumentation and measurement. This was started up recently to look at the topic of measurement and monitoring within the OCP TAP environment, specifically for data centers. My name is Anand Ram, and I work for Calnex Solutions, and we're a test equipment company, which is why we're involved in the field of instrumentation and measurement. So let's talk about the work stream and what's been going on so far. So what we're trying to really do is focus on 3 broad areas of work, and our meetings are focused on these 3 areas. First of all, we're trying to incorporate more testing methodology, or at least standardized or benchmark testing methodology within the OCP community for timing, testing, and measurement. The second is to really create an ecosystem of open source for measurement tools. Today, obviously, as a company building measurement tools, we're also interested in exploring how the open source community can contribute to and benefit from in terms of measurement equipment and tools. And then finally, we also like to be a collaboration forum. Any of you who've ever done any testing before know that you do a test, you get a result, and then you have to explain the result. What does the result mean? What is your next course of action? So we believe, again, there's a lot of opportunity for collaboration here, where different people doing testing of similar nature could exchange information and benefit from learning from other organizations. Today, though, I'll focus mainly on the first 2 of those because we're just starting to get going with some of these broad work areas. We encourage most of you on the call to try and get involved with this work stream if this is of interest, and we can get the 3rd area growing and going a little bit more. Okay, let's talk about the testing methodology. So we've started with focusing on a project, first of all, about stress testing a timing receiver. What timing receiver? Well, the time card, of course, is a major project of this group, is the first timing receiver that we're stress testing. But really, the project is not just to stress test that timing card. It's also to try and write down a methodology of if you have a timing receiver that's going to be distributing timing, what are some of the stress tests that are sensible to run in the OCP environment? So we're doing this using a GNSS simulator and a measurement system. So that's wrapped around the timing receiver to make those measurements. And obviously, we want to focus on specific scenarios that are of most relevance and interest to the OCP community. And obviously, things like spoofing and jamming, as well as degraded signal conditions are of issue here. In other technologies like telecoms, for example, things like multipath and other atmospheric effects may be more interesting. But for the OCP, we look at things like spoofing, jamming, leap seconds, and other degraded conditions. And actually, we did a little bit of work on this. We actually showcased a demo recently at the workshop of synchronization and timing, which is a conference that was held in Denver just last month. And we showcased this demo, which I'm going to talk a little bit more about in the next few slides. And really what we want to try and do is take this, the testing that we did, write up the test methodology so that, and then publish it within the OCP, so that if you're designing or developing or just testing a timing receiver, you can refer to this methodology. And then what we've seen from the telecoms community is everybody is doing the testing the same way. That becomes a benchmark, it becomes a reference, and it helps everybody deploy solutions in a more uniform methodology. So let's talk a little bit more about this project that we did. The test setup really, as I said, used a GNSS simulator to simulate GNSS as well as disturbance conditions. We obviously use the Facebook time card as the device under test here. That was hosted on an Intel NUC. And then we really use the timing measurement system here to measure the quality of the signal under those different GNSS conditions. And fundamentally, we've got different points of output that we were measuring, both from the FPGA, the U blocks, as well as the output from the time card itself, as well as the reference connected up to the test bed. And again, there's more details of this results and information available later on, but just to kind of quickly cover the high level aspect of what happens. Of course, we varied the GNSS and we saw some impact on the timing. We created a spoofing scenario, and once again, not surprisingly, we saw an impact on the timing. And really what we're really trying to do here is measure the time error of the 1 PPS by varying the quality of the signal level of the GNSS, seeing what the impact that has, and secondly, by spoofing the GNSS, seeing what impact that has directly on the output of that time card. And you can see here that there are clearly effects on it. The key here is to try to work out what are the limits of the performance. And that's something that's really going to be for further discussion. What kind of limits can we tolerate when we have these stress conditions? Another test that we did was really spoofing it with a leap second. So we created a scenario where we ran, again, the spoofing. You see the impact of that in the line and the time error jumping up, and then created a leap second, of course, which creates a drop scenario. Once again, this is just starting to show the concepts, which is, again, not surprising, of these GNSS impaired conditions having an effect on the output timing. And ultimately, what we're also hoping to do is try and agree reasonable limits of what they should be, what the stress conditions should be, and what the test limits should be. And this was simulating, as the slide says here, 8,000 second leap second occurrence. The other thing we did was actually trying to interfere and jam the signal. And really what we saw here was that we actually saw very little impact when the interference or jamming scenario happened. So it's pretty reliable and robust under those conditions. So again, and of course we turned off GNSS, and obviously that had an immediate impact at the end. So really, that was really a summary of the project for the trying to write down test methodology. We now just need to write down the test methodology, have a discussion about appropriate limits for that test methodology, and then try and publish more of that work on the wiki. The second area of work that I talked about was trying to create an open source environment for test tools. And again, we've taken the lead project here by trying to use the same hardware I talked about before, using the time card not as a reference source but of timing, but actually using it as a measurement tool. It has rubidium in it, it has a PPS inputs and outputs on it, it has a GNSS reference on it. Can we now use it as a reference system, as a measurement system? And we wanted to run that and do some comparisons with commercially available timing measurement systems that are out there today. And we'll show some of the results of that work. We've done a quick initial comparison. And of course, we want to do more detailed comparison. We want to do more thorough comparison to see if products and designs in the open source community can be leveraged to create instrumentation and measurement tools. And obviously, we also need to further explore the visualization and analysis tools. Again, most commercial measurement systems today have built-in visualization and analysis tools as part of the commercial offering. And obviously, we need to look at how can we do that within the open source community as well. So the initial projects are encouraging. We ran the time card against a product called the Sentinel, which is a commercially available measurement device. And you can see, broadly speaking, you see the results are tracking with each other. Obviously, there are some variations. There's a lot more jaggedy signal as expected on the time card. There is some variation in terms of the absolute results. And really, but this is encouraging information about the ability of the time card design to act as a measurement device. So what we really need to do now is scratch beneath the surface. We need to go in and create different conditions of reference signals, make the measurements against different commercially available measurement equipment, and then publish those results and findings as we develop. So that's really where we're going to focus on next. And that's really broadly an update or bringing you up to date in terms of the work that we've been doing at the instrumentation and measurement group. Number one, we're trying to work on some test methodology to get adopted across the industry for measuring different things. What are the methodology? What are the limits? And then secondly, using open source developments and discussions that are out there to try and leverage that to create measurement systems within the open source environment. So that's really it. There's an update from the instrumentation and measurement group at the OCP. And so I have time for questions. So once again, we do encourage you to join this. All the information is on the wiki, including times for our calls and discussions. Again, if this is a topic of interest to you, feel free to contribute and join in our discussions. And back to you, Elad.
Thank you, Anand. Let's open the floor for questions again. I pasted the link to the wiki page for your work stream, Anand, and thanks a lot for you and the team that you gathered. A lot of progress in a little time. Thank you.
Yeah, no problem, Elad. I'm sorry, my light went off in the room. I was trying to turn it on. There we go. Now you can see me again.
Cool. Okay.
Hey, Anand, I don't know if you can hear me.
Yes.
But this is Bob Nosworthy. I just wanted to ask what type of timeline your group has for first cut.
We don't, is my honest answer, Bob. You know, we obviously, like a lot of stuff at the OCP, we're trying to leverage off people's additional time that they're trying to dig out of their day jobs. But I would say that, you know, we're very keen to try and have some more detailed results on the second thing, which is using the time card as a measurement equipment in the next month or two. I would hope to have some kind of information. Now, that means we have information and we have some instructions on how you do it. Like I say, it doesn't have any of the wraparound in terms of, you know, how do you look at the results, analyze it, visualize it, and so on and so forth. So, but I would say we'd have more data in the next month or two for the time card as a measurement device. I would hope in the next couple of weeks, we can have some documentation on test methodology. And really, we're looking for input from the community here in terms of what kind of, we're just proposing 2 ideas as projects. What are the projects that would be of interest to you? What kind of test methodology and what kind of instrumentation in the open source would be of greatest interest to you? So again, we encourage you to feed that into us. But I would say, Bob, in answer to your question, methodology, you'll expect to see something in the next few weeks from us. In the hardware side, probably in the next couple of months.
Great, thank you.
Okay. So thanks again, Anand. And for the next session, we have the honors to give the mic to our friend Lasse Jensen from TimeBeat. Lasse, you have 10 minutes additional to what you had thought, if you want to use it. And the floor is yours.
Maybe I'll spend the extra 10 minutes trying to find out how to share my screen now. We don't know.
There should be a share screen in the middle. Yeah.
And I got you. So how's that? Is that working? So can you see yourselves now?
We can see you. Yeah, we can see your screen.
You can see my screen. You can see the presentation.
And we can see you.
And you can see me. Okay, that's great. Okay, yeah, so my name is Lasse, and I come from Denmark, and I work for a very small company called TimeBeat, and yeah, we do a product called TimeBeat, and now I'm going to tell you a little bit about some of the interesting stuff we've been working on. But first, seeing as I'm about to lean in heavily into 1588, I guess I would say that, yeah, in many ways, you know, PTP is a considerable achievement, right? There is very broad support for it. let's say in Linux at least, good methodologies for accurate time in the hardware. Okay, mostly every NIC you can buy now has 1588 support and can do at least reasonably accurate time stamping. And also in the network layer, okay, switches and so on, they have PGP capabilities, boundary clock, transparent clock, etc., etc. Okay, and these capabilities are being used to some extent. Okay, historically, I've spent a lot of time thinking about how they're applied in finance. Okay, and here regulations have sort of brought them in with MiFID, and it prevents some of the worst sort of things that used to happen in the past, right? So now sequencing is much sort of clearer than it used to be, right? But it used to be that a brokerage would receive a large order from a customer, and then before they executed the order, they might just do a little trading by themselves in anticipation of how the market was going to move. And you know, having sequencing and understanding of A, B, and C, which one happened first, second, and third, okay, it has made a difference. Okay, so that's good. So overall, I'm a fan. Okay, but now I'd like to talk about some other things I'm not such a big fan of. Okay, okay, and yeah, chief among them is I guess boundary clock distribution, but to be honest, it can also be transparent clock, and let's say how everything, okay, has some single source, single parent principle, right? And yeah, I wrote it in the notes. If you think about this, so here you have maybe and a lot of enterprises work like this, quite frankly, right? And even a lot of, you know, value-added service providers, they have networks like this. So you have some grandmaster clock, okay, it gives time to a boundary clock layer. So this is maybe different switches, right? Where one switch gives time to the next layer, which gives time to the next layer. And then at the end of it, you know, sits some servers, okay? And we talked about a great many technologies today, but the reality is that these servers are kind of stupid, right? They only have like a PTP capable network card, right? And if they're VMs, they might not even have that. And the problem I have here is that everything, okay, is a single point of failure here, okay? Because if this guy does not manage accurately to synchronize you know, the pulse that comes out of the GPS chip with the oscillator or the PHC, right? Or if there is, you know, a cable between the grandmaster here and the first boundary clock layer, which has maybe two different types of SFPs, right? Then you have some asymmetry introduced, right? Or if you know, the servo inside the boundary clock switch, okay, it's not as good as it should be because, okay, maybe it was not the specialty of the people who made the switch to develop this. Or, you know, if there is a layer of switches in between which do not have this capability, or if network buffers fill up with traffic, or for, you know, 10 other things, the reality is that everything here is a single point of failure, right? And there is no way to quantify this error in the downstream network. Okay, so if you have something in the upstream that introduces an error, there simply isn't anything in PTP that that is sort of able to tell you that that's going on, right? And I think this is an enormously big problem. And I think as fantastic as it is that we're coming up with more and more solutions for individual problems, when we look at it overall, I'm really concerned about this. So there we go. So that's me. And yeah, here is sort of a more real world example, right? Where we can see the same thing. And the question then arises when all of this has been set up, okay? So does this server here, okay, have the same time as this server here? And with the classic model, the typical answer when you ask someone is, well, that's the assumption that we make, right? We think that's the case. But then when you actually go out and you try to find out, if that's the case, very frequently it turns out, no, actually they don't have anywhere near the same time, right? And it's because somewhere in the upstream, there was some asymmetry or some problem that led to this, right? I mean, I know of cases where, switches in the boundary clock layer went into holdover and nobody realized, right? And so when you measure it, you have these enormous differences. And that's a problem, right? Especially if, for instance, in financial regulation, you're sort of obliged to actually know, right? And so if you don't, if that's a problem, this is not so good. And I sort of suspect a little bit that what happened was, and I can remember like half a decade ago, being in the millisecond range, right? And then things improved and we got better writing software and switches got better, and NICs got better, and everything got better. But as we moved through this chain to microseconds and nanoseconds and now picoseconds in some cases, right? If companies that are doing high frequency trading or say where low latency is relevant, okay, to benchmark whether they managed to do some optimization, right? Picoseconds is now sort of the place to be. So anyhow, so then I thought, okay, great. So how can we do something about this, right? And so we thought like it would be more interesting, okay, if instead of sort of every node in this distribution tree had only a single parent, right? And this is really the case, right? Because you can also think of a best master clock algorithm, okay, and sort of the way it works and the perversity of that whole system working on the basis of self-reporting, right? If you have two things which are sort of giving time or have the capability of giving time, okay, it's up to the individual clock and so on to say I'm the best. And this is not a good strategy. So we thought about, okay, let's turn it upside down. And then what we did is we give every server sort of access to an upstream tree that looks like this, right? So if we have a server here, he has the capability of getting time via this path, or he can get it via this path, and so on. And the way we optimize this in what we call PTP plus squared is we actually look at the distribution of offsets between every hop, and then we calculate the standard deviation and we pass that downstream, okay? So there, okay, now you don't have a single parent, you have multiple paths, okay, that you can compare, and this is much more interesting because then you get an idea of whether you're right or wrong. And actually another part of this is we also distribute time, and then we have those sources tell us, okay, how is that going with reference to where else they're getting time from. But we have only 20 minutes, so so it sort of looks like this, right? So when we get out of the PowerPoint world and we look at, okay, what does the system that we've created look like in the real world, okay? We have here, so we use Grafana, right? And we've made some D3 based cool controls, okay, to visualize it, because otherwise my explanation would never suffice, right? So in order to understand it, we needed something like this, so you don't just get it from me. But what you can see there is essentially different now. So each of these edges, each of these names, we could call them vertices, different city names is actually a server, right? And then It takes time from some other servers, okay, and it gives time to some other servers, okay, and you can see the edges between between these vertices, okay. Some of them are sort of solid, and some of them are perforated, and you know, this is about which ones are we observing and which ones are we actually using for synchronization, right? But the benefit is also that if we have, because it's all based on these this cumulative variation, which is sort of communicated down this directed non-acyclic tree that we create, right? The benefit is that if all of a sudden there is some problem in the network where maybe there's network congestion and consequently, you know, the error of a particular source goes up as a result of this, okay, then nodes which are downstream from that can immediately switch to other paths around this problem, right? And that's kind of cool. And yeah, here's another one of these controls. So here, okay, we have all of those same nodes again, right? And okay, it's speeded up a little bit, and but what you can see there is really that each of these nodes, you see how there's 3 numbers in each bubble, right? And yeah, in the newer ones, we passed it through a nicer format, right? But essentially what that is the upstream cumulative error of different paths available to a particular node. And this gets optimized sort of all the time, right? So different nodes that have different capacities available send information around the grid about you know, how well you know, their upstream paths are, and then if it turns out there's a node somewhere which has less error to you know, some source of UTC somewhere in the network, and this could be from GNSS or whatever the case may be, okay, then it can converge around around those nodes instead. And so this is really why all of this is sort of changing as we're looking at it, right? Because the network is optimizing itself all the time. Okay, and yeah, then we have just let's say this does not have to be the this can be an addition to other stuff as well, right? So you might have, for instance, you might maintain, if you want, the existing infrastructure. Okay, so in the classic enterprise, it could be the boundary clock model. Okay, at the hyperscaler, okay, it can be that they tend to enjoy more building the largest monolithic distributor of chime in the world, and then have a layer of switches that does transparent clock in between, and you know, that's all fine. But all we're saying is you can also let the sort of these nodes, right, that are ultimately consuming the time, do a bit of communication with each other, right? So they can compare time, because you really get the because it becomes essentially a lot more difficult for asymmetries to have somewhere to hide, right? If we do this type of structure. And also on top of that, we do lots of other things, which includes like monitoring what are the outputs of servos, right? I mean, if you're only really concerned with looking at something like the offset that you are measuring in the P2P calculation between yourself and something else, you know, you might miss a trick, right? I mean, if you have a good servo, I can sort of oscillate the time from plus 500 microseconds ahead of UTC to minus 500 microseconds behind UTC, and you will never discover it if you're just looking at the offset, because the servo sort of keeps up all the time, right? So that can be interesting to watch. And then other things as well, right? PHCs and how they're getting synchronized, and how a lot of the error is introduced there. And you could also have, so for instance, service providers who have this boundary clock layer, they sort of like if, you know, we compare the time that comes out of these band rate clocks with some type of independent reference source. Okay, so you can have that as well if you want. Okay, and then yeah, what are we looking at next? I thought I would just discuss this. Currently, TimeBreed is you know, a closed source freemium piece of software. I'd like it to be open source. Okay, we're sort of at the moment trying to nail down what's the best approach to do that. I hope, okay, we can get somewhere on this, and then TimeBreed will be free and also open source, and then there are lots of benefits on that. You know, some of it is people trusting more the software if they can see how it's written, and also you get lots of contributions from, you know, other ClockSync enthusiasts. So that's good. Like has been discussed by several other people today, I'm also keen on working on this problem with, you know, finding out the precise offset between a PHC and, you know, the clock, the kernel clock, as is a product of the CPU timestamp counter, or the tick counter in the CPU. Because the reality is that today, a lot more error is actually introduced, you know, in the 4 centimeters between the CPU and the NIC than between 2 NICs that are thousands of kilometers apart, right? And some of the solutions to this, including daisy chaining NICs with PPS and so on, is absolutely hopeless. So I'm not yet a believer in PMT, but I hope I will be. I think it sounds very cool. You know, who knows? And then, yeah, I'm also looking at, you know, how can we improve the performance of, you know, user-land PTP stacks by taking advantage of kernel bypass and some of the features which are sort of available in NICs now, because they're getting more advanced. And then we're going to do some boxes that look like this. Okay, so because I don't believe in this very monolithic sort of single end model with 1 or 2 traditional grandmaster clocks, okay, we're doing things with, this is actually a commodity HP server, okay, with an OXA from Chemical Jackson Labs and different types of NICs. And there's even going to be a low end of this, which is going to be based on, you know, a Raspberry Pi, a CM4 that I've recently done some work to add 1588 functionality to, and things like that. So yeah, so that's what I'm up to.
Thank you, Lasse.
Hey, you're welcome.
Let's see if we have any hands raised. And there's a question from Dan Biederman. How many clocks should a node maintain for time as a service? Is 2 enough? 4 more?
Okay, yeah, so this is a good question. So 1 is definitely not enough, right? Because 1 is the equivalent of walking down the street and asking a guy what time is it, and they'll tell you something, and you don't really know. He could be lying to you, right? Or he might just not know. And then if you have 2 sources, the problem is that if they don't agree with each other, well, then you know you have a problem, right? But unfortunately, you don't know which one of them has the correct time, right? Whereas if you have 3 sources of time, you know, you then, and you have an outlier, then, you know, depending on what the other 2 say, you can be reasonably sure which one is the outlier, right? And actually, this is also why in TimeBreed, you know, you can add as many concurrent sources as you want, and from second to second, we then determine what is the genuine offset on the basis of the median value. Okay, so if you have, you know, 3 sources, 2 of which have approximately the right time, and one that thinks it's 1985, you're in no way, shape, or form affected by this. And also, by the way, then you can generate an alert, right? And say, actually, this other server which is reading me some time, could be that someone should just have a look and see why it thinks it's 1985.
Dan, does that answer your question?
Yes, thank you very much.
Okay. Any other
Yeah.
comments?
Yeah, and by the way, like I said, if you want, you can go onto our website and download this. So if you have 10 servers and you want to play with this, you can download it and install it and see how it works.
Okay. Thank you, Lasse. Our next speaker is Diman from Trimble.
Thanks, Elad. So just give me a second here. I will bring up my slide deck. All right, so I am Diman Chaudhary from ProTempis, formerly Trimble's Time and Frequency Division. Today, I will be joined by one of my colleagues, Christian Boyd, who manages field application engineering for our EMEA operation.
Hello.
So I'm trying to bring my slides
yeah, I hope you can hear me well.
Yeah, thank you, Christian. For some reason, my slide deck is not moving.
Oh, maybe because I'm sharing it.
Oh, you are sharing
I'm
it.
sharing mine,
Can you move
sorry.
to the next slide, please? Thank you.
Yeah, sure.
So since this is our first time, so let me take this privilege to introduce our new brand, Trimble's Time and Frequency Division, which is known for its services. 35 years, we have provided services, time synchronization services to the industry. We have deployed millions of devices to the various different networks, whether it's a telecom radio unit to industrial automation to the newer development of autonomous vehicles. We are providing time synchronization services there. So Trimble's Time and Frequency Division has now become a ProTempis as a standalone entity. It is our new brand, but nothing changes. We bring in the same legacy of serving our customer closely to the marketplace. Just wanted to take this privilege to introduce the new brand. As you are aware, that time synchronization is one of the two critical imperatives. Another imperative is latency. So without these two key imperatives, today's modern network would be difficult to operate. And many of the technologies that is currently being used, for example, let's take 5G for an example. 5G spectrum uses TDD, time division duplex. So without precise time synchronization, 5G's front haul operation would render into a failure. And in some other network, for example, industrial automation, one of the critical elements is time synchronization for the deterministic network that industrial automation uses. Deterministic network has two elements to it. One is how do you create the flow control and guarantee the transport? Another aspect of it, how do you precisely synchronize all disparate devices out there? So this chart shows you various different networks and various different applications, how they are using time synchronization, what is the minimum requirement for this. As you can see on the data center side, it's on the right-hand side, data center can be somewhere from sub-microseconds to milliseconds, depending upon the application. For example, in a modern telecom cloud environment, data center being extended out to the edge and providing edge cloud and sometimes MEC services. For that purposes, you probably need sub-microsecond level accuracy. As opposed to in data center where traditionally NTP was being used for millisecond level accuracy, right? And that part is also changing, as you have seen from the TAP implementation and the time card being proposed. That is potentially will bring down from millisecond to probably tens of microseconds accuracy for the data center. So this chart kind of gives you a understanding of which application requires what type of timing accuracies. So how do you, next slide, please, Christian. How do you use time synchronization?
Not sure why it's not. Just a second, I'm trying to. Oh. Sorry.
Can you release it? Let me share.
Yeah, it doesn't want to. Let me go to the next slide. Something is blocked here by this annotation thing.
Okay.
How do I do that?
Okay, let me share this now.
Yeah. Okay.
All right. Excuse us for this. Hopefully. So as I was saying, to provide time synchronization in network, you have two choices. And you need to have a UTC compliant time source, a stable time source, but you have two choices, whether you are using atomic clock or GNSS time synchronization. The time need to be stable. For atomic clock, atomic frequency has been a standard for time synchronization. And that time synchronization has been distributed through atomic clock's time server or atomic clock radio signals. But this proposition of providing synchronization to the normal network services is quite expensive. But the similar frequency standard you could able to provide through GNSS system, and that is very cost effective. And modern infrastructure increasingly using GNSS time synchronization as a service. So the GNSS time being obtained through GNSS system, and GNSS system has three parts to it. The first part is space segment. The space segment includes satellite constellations, and there are different kinds of satellite constellation. Here is what I'm showing is what I'm discussing here is GNSS, which is Global Navigation Satellite System. And global navigation satellite systems resides in a Earth orbit that is between 10,000 kilometer to 20,000 kilometer. And it is known as medium Earth orbit. And this is traditionally being used as a standard time source because these satellites, MEO satellites, has an onboard atomic clock, and it is reinforced from the ground segment, which includes the control stations. So these particular satellite systems has been used in the industry for so long, but there is a new entrant to it, a new competition to it, and that is called LEO satellites. LEO satellites are generally in low Earth orbit, around 160 kilometer to up to 10,000 kilometer. But majority of the LEO constellation available today from SpaceX and Global Star and other provider, those constellation services not having an atomic clock on board, and they cannot provide the PNT services. They are basically for broadband services. Now it is possible for them to synchronize from the ground segment and provide the clock through their signals, but that is not the main purpose for those satellites. A group of startup companies are coming up to provide LEO PNT services. You probably heard of some of the companies' name, but their constellation is not out there to support. because at a given point, due to the speed of the LEO satellites, you need 16 satellites to multilaterally provide the accurate clock services. So you may have this question about the LEO PNT services. It will take few years for you to attain the benefit of having a accurate clock services. While that is not there, today GNSS is the best solutions, and the GNSS, as I mentioned, 3 segment. User segment comprised of GNSS receiver that goes into various different systems, right? Having said that, let me bring in Christian Boyd. Christian, go ahead and pick up the slide from here on.
Yeah, thank you, Diman. Yeah, let's take GPS as an example of one of the several global navigation satellite systems, such as Beidou and GLONASS and Galileo and Navig in India. What I heard today in several presentations are a lot of interesting keywords, and to me, much of that comes back to the traceability of the time to the truth. And the truth is actually the International Atomic Time, TAI, which is the base of the UTC. UTC is the time system we are used to work in, the calendar and 24-hour clock system, but TAI is actually the base of that. And that is a time maintained by the TAI and UTC clock ensemble, which are hundreds of clocks in national institutes. And they are all steered with some steering offset towards each other, and an average is being built. And that average is the only truth. So there is no other truth. And the question is, or the assumption is, in a grandmaster, that you have a true time. But how do you get traceability from that international clock ensemble to your grandmaster? And here's a chain of traceability based on the GNSS, based on the GPS example. So the NIST clock, the National Institute of Standards in the USA, is among the clock ensemble that provides the TAI time to the world. And the base time for the GPS system is the US Naval Observatory clock, the so-called USNO clock. That is directly linked to the NIST clock, and it is also part of that TAI clock ensemble. Now that clock is the base of the ground station segment for the GPS system, and the big block here on top, that represents a space vehicle, the actually GPS satellite, that is getting the time synchronization from the ground station control system. And that satellite sends now the radio signals, basically time-tagged radio navigation messages to the GNSS receiver, which is the small module here on the bottom. And yeah, 20,200 kilometers of travel time are basically free of error. The last couple of tenths of kilometers contain a whole lot of errors. Demand, would you go to the next slide, please? I would like to focus today in this presentation on the advantages of dual band timing receivers, which is actually what we have on the time card. One of the 2 modules is ours, and we are using a L1 plus L5 receiver on that board. And I would like to explain to you why that is so advantageous for the corrections of those errors that happened on the last few tenths of kilometers of the travel distance. Because the biggest contributor of errors are, there are actually 2 error contributors. One is the pass through the atmosphere, and the main contributor here is the ionosphere, which is an electrically charged layer. And that or it can be multiple layers actually, but those layers act like mirrors for the GNSS frequencies. So the travel path is reflected on its path through the atmosphere, and the receiver needs to compensate and correct those ionospheric errors. And the common method of a single frequency receiver is that it has a mathematical model of the ionosphere, and it computes corrections based on that mathematical model. Now, how good that compensation is depends on how good that model is. And the ionosphere changes dynamically because it's created by sun radiation, which hits atoms in the upper atmosphere and ionizes them. So at daytime, this electrically charged layer builds up, and at nighttime it decays. So it's a dynamic model, and there is no way that the local model in a single frequency receiver can be real time and so accurate as the real situation is. But if we have a dual frequency receiver that can receive signals on the L1 band and signals on the L5 band or some other band, then we can actually do real-time ionospheric error measurements. That means dual frequency comparison measurements provide us with the real offsets that we can subtract in real time and correct as a known error from the time computation. And we can do that because the travel path is affected in different ways on different frequencies. So by having two different travel paths, we can come in real time measure and correct this ionospheric error to the most extent, much better than any mathematical model can do. Now, why are we using the L5 signal, which is a relatively new signal, and just I think last week was the 5th GPS Block 3 satellite being launched. The Block 3 satellites are those who are capable of transmitting the L5 signal, whereas the L1C signal is one of the original GPS signals which carries the military codes as well as other commercial codes for traditional dual frequency receivers. But the big advantage of the L5 signal is that it has actually twice the signal power of L1 and L2 signals. And by that, we have a much lower risk of interference with other sources of RF, and it can improve the multipath protection a lot. The multipath is the other big source of error on top of the ionospheric error, and that multipath happens actually by natural or man-made objects on the ground level. So let's take an urban canyon, for example. You have a lot of big buildings with big facades, and they mirror the signals. So the travel path may not be even direct line of sight. It may be just a pure reflection, or it can be a mixture of direct line of sight and reflected signals. And the receiver needs to deal with that. So by having a stronger signal and by seeing two different frequencies and two different data scheme codes on the two signals, the receiver has a much better input to detect and compensate for multipath errors. On top of that, the higher signal strength also allows the receiver to do a much easier acquisition of the signal in unfavorable conditions, like in obstructed conditions. And also the L5 code has a civilian code that is 10 times longer and 10 times faster than the standard L1CA code. And since the maximum resolution for the pseudo-range measurements is typically 1% of the chipping rate, the faster the chipping rate is, the better we can get the resolution of the pseudo-range measurements. And we can also resolve the ambiguity in the signals, for example, millisecond errors that happen eventually with L1 signals if you are not able to resolve the ambiguity properly. Also, unlike the L2C signal, the L5 signal is a safety of life signal approved by the ITU-T for aeronautical radio navigation services. So that band is protected against interference from other commercial services. So no one is allowed to use services in that L5 band. That makes it pretty safe to use internationally. And the last point here, the wider separation of frequency between the L5 and the L1 frequencies compared to the L2C and the L1 frequencies, that gives us a more a better input to allow for better anti-jamming and anti-spoofing performance. Anti-spoofing is actually the thing that I had in mind when Kevin Stanton was talking about the Ethernet time, and Dotan Levy was emphasizing the reliability and the accuracy of the measurements, because spoofing and jamming are big contributors, especially spoofing. And unfortunately nowadays, malicious individuals and also unfortunately countries and some governments, they attack the systems intentionally. And it is becoming much more important to have receivers that are capable to detect spoofing attacks as well as jamming attacks. Demand, would you please go to the next slide? I'm a little bit short with time here. Hopefully I can speed it up a little bit. So by mitigating the multipath and spoofing, we are able to get a much better integrity and reliability. And I think that is a very important thing also for the data center application, because, for example, when I look at the fail-safe operation and the robustness against attacks, we have a much better protection against those things, because we have actually 25 validity indicators in our new L1 and L5 receiver to provide detailed information of the current signal conditions. We can do that per satellite, per constellation, and per the combined solutions. And next slide, please. This is our receiver that is on the time card, on the second receiver card, a new version of the time card. And you see the features that we have here. It's a multi-constellation receiver with dual band, 10 megahertz output and PPS output, and synchronous within 5 nanoseconds, 1 sigma to the GNSS system time. And one thing that I would also emphasize here is the secure boot feature, which addresses the fail-safe programming that Dr. Levy has brought up in his presentation. I would like to spend more time on that, but we don't have the time now. But secure boot actually features multiple firmware images in the receiver, and we only switch to the new one if the new one has been authenticated with encrypted and signed keys. So this is a very secure way of making sure the firmware is intact and not manipulated. Demand, next slide, please. This is to show you our product portfolio, and I'm not going into detail here now, but you see we have a lot of different types of products, for example, with and without holdover, with single frequency, with dual frequency, with PPS, and in addition with 10 megahertz. So it's a wide portfolio. We have a very long-term experience with receivers. And well, actually the one on the time card is our latest and greatest product. It's the RES 720. And yeah, I think with that, I would like to give back to Diman for the rest of the presentation.
Thank you, Christian. Just to summarize what Christian said, that from GNSS receiver point of view, if you are trying to determine what kind of receiver that you choose, it depends upon what type of environment that you are in. For example, telecom environment where hacking is a bigger concern, given that today's geopolitical scenario, a state actor may come in and hack the communications as well. So in that scenarios, it's better to have a dual band where you have anti-jamming and anti-spoofing capabilities. If one signal being macroned, you can fall back to another signal, and also multipath situation that is also as pretty good performance is pretty good. And another thing is with the dual band is that if you are looking for L2C versus L5, I think the better choice is L5 unless you have a triple frequency support in the receiver, because L5 has less interference and L5 is approved by ITUT. So that was the summary of those slides. So from the portfolio standpoint, ProTempis also provide time server portfolio. We have a grandmaster boundary clock and time NTP time servers. So this is kind of a summary of the timing GNSS timing receiver, whether you're looking for L1 single band L1 or the dual band receivers. These are some of the portfolios that you could work with. So this is an example of how you could use, you could have a seamless integration with your, this example shows cell site router and how ProTempis RAS 720 or ICM 720 can be used with the processor to provide stable clock services. Now, when I'm talking about stable clock services, GNSS receiver, though provide stable clock services, there are other ways to get stable clock services. What we call is a GNSS DO. Here I'm showing the OCXO separate from the ProTempis RAS 720, but if you combine the two, that becomes a GNSS DO or GNSS discipline oscillator, or you can call it, what we call it is a discipline clock, provides a stable clock services to your embedded system. So as of May, I mean, we have been working on this from March until today. Our RAS 720 on a standard carrier board is used in the time card, and the performance for the PPS was pretty good. So I just wanted to bring in that aspect of it. So having said that, the different kinds of scenario where you can use RAS 720 or any other receivers for that matter, what I would like to emphasize here is a sync plane design, whether you are designing for data centers, whether you are designing for telecom cloud, industrial automation, autonomous vehicles, a broadcast network, and so on and so forth. What is important here is that it can get very complex. And for scenario where sync plane design is very complex, you can opt relying on some of the vendors like ourselves. We work closely with customer to provide sync plane design solutions for them through our product. Having said that, thank you. If you have any questions, please bring it up.
Thank you. Thank you, Christian and Diman. We're just the top of the hour. No hands raised. So with that,
maybe let me add a final comment, because I think that really one of the key things is what Anand Ram has mentioned, because the problem here in spoofing and reliability is the lack of defined test methods, and that is something that I think we need to collaborate in this platform, because having some way to test the robustness of the entire system is really critical, and I really would like to take that opportunity to close up with Anand and work on that.
Awesome. We welcome this collaboration, and please reach out to Anand. Appreciate that. Ulas, I see your camera is open. You're up next. Yulas is coming from Rican. Please introduce yourself and go ahead with the presentation.
All right. Thank you very much, Lad. Can you see my screen?
Yes, we can.
Okay. So thank you for giving this opportunity. The topic today is choices for 5G data center synchronization. This is more from a reference sources perspective. As we understand, most of the node clocks will be steered through a local time source by cleaning up some upstream clock, like a GNSS clock or a PTP clock or a physical layer clock that comes in, and probably traceable to a primary reference clock. So it's mostly the talk today is based on reference sources perspective and how the choices of having them on the data center synchronization. My name is Ulas. I'm from Raycon. We make oscillators for telecom, datacom, PNT, aerospace, and defense. And we specialize on IC-based mini OCXOs, which uses crystal-based MEMS technology, MEMS resonator technology with high reliability and things like that. This presentation focuses or introduces some of the upcoming synchronization scenarios and the key performance parameters that we should be looking for, and possible reference clocks that we might have. Fundamentally, we have this DC profile defined by the OCP tap, and we have a hypothetical reference model defined with something like a 5 microseconds end-to-end time error. As Dotan mentioned earlier, there are much more exciting applications that probably require much more significant synchronization performances. For example, the way TSN is going to turn out and how the data center can play a role in building up TSN with the industrial automation and the 5G networks. Even better is the way that ORAN is defining the new front haul, opening it up for more players to be in with open standards, and the DU and CU functionalities moving more into the data center, driving the data center synchronization to be much more stringent than what we have today, or increasing the importance of telecom data centers in the world of telecom. When we look at the key parameters for synchronization, we can probably look at two main things. The first part is the dynamic performance of the system. When we say the dynamic performance, we can think about this as a servo system that filters the network noise and or combine that with the oscillator or the local reference clock error. We'll get into the details of the oscillator error later, but we can understand that the network noise means the maximum network limit. That's the standard term that is used in many of the standard bodies. And based on the hypothetical reference model, there's a limit of noise that is defined that can get into any of the network equipment. And that is filtered by a filter. And this filter is also generally defined in the standards. And combine that effect with the reference clock noise. So that's one part of the key parameters that we should be looking for. In many of the standard bodies, we can see that the reference clock error is based on the environmental factors. And mostly that is based on temperature for short term. And that's one of the key parameters that we should be looking for in considering the dynamic performance. The second part is holdover. I think most of us already know about this in detail. It is the ability of a clock to hold its output within certain limits for a certain period of time when all of the reference clocks are lost. So from a reference clocking perspective, these are the two key parameters for synchronization that we should be looking for. To get into a bit detail on the dynamic error, we can generally visualize a servo system as a with different components comparing, say, the initial part is a phase comparator that compares the network clock, the primary reference traceable network clock into the local reference, and then it will generate a error that is the difference between the local clock and the network clock, and then that gets filtered depending on how bad or how good the network clock is, and then that gets driven into a VCO or an DCO that is driven by the local reference oscillator. So this way we can see that the network clock steers the local oscillator to get the output clock. The loop filter actually filters out the noise that is in the network. At the same time, the filtering happens, or filtering requires, or the filtering is defined based on how much noise that we want to filter out from the network. So the impact of that is a high pass effect of the oscillator appears on the oscillator or on the servo system. If you think about it, if you look at the say diagram here with the oscillator noise represented as a linear variation from nominal, and if you think about the correction intervals like that, once we start the system will move with the oscillator, and at the correction interval, the servo system will bring back the error into nominal value, and we probably can assume an output error like that. So if you have much faster correction intervals, then we can see that with the same type of oscillator error, you could have a much better or much lower output error compared to what we have in this scenario. So the question is, what is that is determining this kind of variation on the oscillator? So for short and medium term, this is mostly driven by the temperature impact of the oscillator. There could be other impacts, but the most prominent effect is based on temperature. We could also see that if we were to have a similar output error as the low bandwidth filter like that, then the oscillator had to be much more stable. And that's the crux of the problem that we are determining here. So depending on the output error that we need, based on some kind of a dynamic error, we could call it the time error that we need, we can define, or there could probably be some recommendation for the loop filter. We should know what kind of network clocks, that network clock noise that is coming in. That depends on what is the kind of network that we have. Do we have one grandmaster and then only one switch, multiple switches, physical error support, no physical error support, GNSS coming in? So depending on all these scenarios, we need to determine the loop filter, and that's what we describe here. If you look at a number of the endpoints, including the radios, we are looking at probably like 5 to 20 nanoseconds error. And some of the loop bandwidth requirements are like, say, in the sub 100 millihertz range. If you look at the switches from defined by the ITU-T in terms of the type C and type D, they need to have 5 to 15 nanoseconds error. You could also, if you read the fine print, you could also see that you have a requirements with respect to the constant temperature and with variable temperature. That's exactly where we need to look at what we need to put into the system in order to meet the requirement. And some of the front haul clock requirements need such small time errors. And if you look at the G.8260, 73.2 like clocks, if it assumes physical error, then the bandwidth of the physical error can be smaller. If there are no physical error assistance, then that gets into the assisted or partial timing support clock. In the assisted case, we have the GNSS inputs coming in. In a partial timing support case, many of the recommendations or many of the implementations use much lower than a millihertz loop bandwidth in order to filter out the worst case packet errors, packet variations, and achieve 5 to 20 or 30 nanoseconds numbers. If you look at the GM clocks, I think I should improve my presentation after hearing from Trimble that the numbers are much lower. We are talking about 5 nanoseconds errors, but the reference input filtering needs to be much smaller, probably also in the 1 to 30 milliseconds range. So if you look at the fundamental of the reference clock that needs to meet this is the variation that happens in the short and medium term. And we can generally classify that into some kind of a ppb per degree Celsius, with respect to temperature again, variation, what we call as the frequency sensitivity. And if you look at the possible choices, we have devices that are controlled. If you look at, say, oscillators, they are probably, some of the crystal-based oscillators are for surely some of the pure sine wave generators. And then there is also other kind of, resonators such as silicon-based devices. But they all do a temperature compensation to get to a much lower frequency stability. We have now hybrid devices. Hybrid TCXOs are between the temperature compensation and oven compensation. What oven compensation does is it will heat the resonator so that the impact of the external variations are minimal. The heating is done in such a way that the ovens are outside the operating temperature range. For example, if we were to support, say, -40 to 85 degrees of operation, the ovens will be at, say, 92 or 95, so that the impact of -40 to 85 has minimal effect. So hybrids are somewhere in between. And some of these devices provide significantly better than the required performances that we were seeing in the previous graph. Moving on to holdover, I think most of us are familiar with a generic deployment of a state-of-the-art network synchronizer clock. At the bottom, we have the physical layer support. Then we have the PTP-based, say, protocol layer PLLs, and then probably the GNSS-based clocks. So in general, we can say that if the physical layer clocks are present, then we need the oscillator to be simple enough that the reference for PTP now comes from the output of the physical layer. So if you look at long-term frequency stability, the physical layer has a long-term, much better long-term stability because it's synchronized to a primary reference. But for short and medium term, you might still want to use the higher stability oscillator because the short, in the short term, the network clocks may be moving around a lot. But the key point is also that if you have a GNSS system coming in, then you might want to have a higher stability oscillator than what is required for a basic, say, physical layer clock like a G.8262 or a G.8262.1, the Ethernet equipment clock or the enhanced Ethernet equipment clock. The point I was trying to say was that the holdover has different meanings to different people. Sometimes we say when the GNSS clock is lost, we call that the PTP assisted holdover. When the PTP is also lost, we call it the SYNCI assisted holdover. And if the physical is also lost, then that falls back into the basic oscillator based holdover. And we all know we have these equations that talks about the servo part of the error. So servos will have the initial phase offset and some probably the frequency offset from the residuals from the servo. On the other hand, there are major error that comes from ones that is with the state-of-the-art PLLs, the PLL-based or the servo-based error are much smaller, whereas all the weight falls back into the oscillator because the environmental factors, the systematic variation called aging, the random noise of the oscillators all contribute to the holdover. And if you look at the choices of those, we have now crystal-based, quartz crystal-based devices that are providing significantly wide range of holding possibilities at much smaller sizes than they used to be. The mini oven control devices now can provide something like a 3 to 4 hours holdover in a 7 by 5 millimeter footprint. Moving up, we have smart OCXOs that does post temperature compensation, which can provide 6 to 8 hours holdover in a standard Stratum 3E 25 by 22 millimeter holdover. Even better, we are talking about PPS disciplined oscillators, either from a GNSS or from a system 1 PPS output, and then accepting the 1 PPS and then doing the aging compensation along with the post temperature compensation, providing up to 24 hours of holdover by taking out the aging and significantly reducing the temperature. So such choices are available for system designers to look at and consider. So thank you. I wanted to summarize. There are new applications and possibilities that drive very high performance synchronization. Dynamic performance and the holdover are the key parameters that we are looking at. And depending on the requirements, there's a variety of synchronization reference technologies and products that are available for you to choose from. Thank you very much.
Okay, thank you. Thank you, Ulas. Thank you for running our last session for today. And it's the wrap up time. If you can, everyone open their videos, we will see our volunteers, OCP members, speakers, listeners. Thank you everybody for attending today, for your attention, for your feedback, and also a round of applause to all the speakers who created this beautiful content for today. I want to emphasize.
Maybe we can have everyone's camera on, so we'll have a group picture. So
yeah, let's do that. Turn on your cams.
Let us know when we have to smile.
While you guys are popping up.
The smile is a very short-term smile, I guess, right?
When you guys all pop up for the grand photo, I wanted to say that, you know, here at TAP, we're trying to be practical, and that, you know, the real live problems that we are facing with our existing deployments, with our upcoming project plans, these are the stuff we want to work on. These are all work groups intended to bring impact, and we encourage you all to join and bring those hard problems to us. That's what we are here for. Pictures are taken, I guess.
Pictures are taken, awesome.
And if anyone has other remarks or questions, the mic is open, cameras are open. Let's go for it.
I have a question. Maybe I'll start. Actually, this question is probably for Kevin Stanton, but after he answers, maybe anybody that's interested can chime in. I'm just wondering, in the next 8 to 10 years, say 2030, 2032, do we all expect 1588 PTP to be the dominant synchronization, or is there any threat coming ahead that could displace it? Any thoughts on that?
Yeah, just briefly, I think the big innovation brought by 1588 was A, hardware timestamping, and B, residence time correction, BC or TC. Those are just fundamental methods of improving the accuracy over packet networks. So unless we have a way of getting wireless GPS into buildings and so on, I think it's going to be the network. It's going to be hardware-based timestamps and residence time corrections. And then the rest of it is just all of the glue around that maintains our holdover and better precision. And I don't think of it as any threat for 1588. I think it's pretty much unless there's a fundamentally different method that's invented, I think 1588 has good legs.
Thank you.
Can we also ask Sven? I think Sven is the right person to add probably some white rabbit representation here.
Well, Maciek would be the right guy from CERN, so, but I mean, I definitely have the feeling that White Rabbit will also have larger deployments because of the need of sub-nanosecond accuracy for a lot of things that are coming up, which we probably don't even know what requires sub-nanosecond accuracy. I mean, CERN, of course, needs it. High frequency trading is close to it, so let's see.
Yeah, and I think the White Rabbit, the high accuracy stuff is now part of 1588, driven in large part by Maciej of CERN.
Yeah, so that's now high accuracy profile, the White Rabbit.
Yeah. I think with the latest changes, I mean the PTP 2019 and how broad the profile can define things, I don't see anything coming up that is going to not fit in that category. Pretty much like PTP made itself future-proof, you know, it's like, okay, anything that comes here, we're relevant, which I think it's very nice.
And also PTP is so remarkably similar to NTP, okay, which has existed since the 70s. So yeah.
So the way that I see going forward, the future of network by default right now is too much asymmetry on the network, and P2P has a challenge and specifically the server level. Jitter and latencies and the traffic not being guaranteed, P2P has a lot of challenge, but P2P is not going away anytime soon. What's going to happen is P2P, like on TSN, there has been work towards bringing much more determinism onto the network. And deterministic network is going to be probably the future, it will define the future of network. And determinism, what I mean is the guaranteed traffic transport, which is not happening in Ethernet-based asynchronous network. But this would be some of the work going forward that industry will do to bring in a little bit of guarantee, because if you look at the traffic from the edge point of view, the push is towards the edge, right? So real-time processing and everything need to happen on the edge. And from that perspective, determinism is important because real-time persistence and near real-time traffic data processing requires little aspect of determinism. And I think the PTP going forward, as on the TSN side of the world that IEEE is working on, to bring a little bit of determinism to the PTP would be a good way of solving future issues. That's what I think would, just an idea.
Hank has his hand up.
Yeah, okay. Yeah, I'm from Clockwork Networks, and one of the issues brought up was asynchronicity. We do measure that. We've got a different method than PTP. It's more of a network, maybe you could call it a network mesh approach, where we measure and can accurately measure the true one-way delay as opposed to PTP and NTP, which do measure the round trip and divide by 2 to get it. So there may be some things coming up in the future that are different than PTP. Even NTP, for that matter, is going to start approaching PTP. It's picking up a lot of the goodness from that, of hardware timestamps and some other things.
One question, Hank, would that, do you see, like, let's say with, I'm assuming this is Huygens, right?
Yes, it's the commercial
version of Huygens.
It's a commercial product based on Huygens.
Yes, yes. So would you see a convergence of the two, like perhaps, because from what I understand, I mean, everyone loves more precision. So from
what I've seen in the industry, The answer is yes to everything. Some people are going to converge, some people are not. You know, we do take advantage of PTP links when they are when it makes sense.
When they're available, yeah.
PTP was, you know, originally it was meant to be on one of those big yellow fat Ethernet cables for a single segment in the manufacturing sector, and it just grew. In data centers, it's been kind of shoehorned in there. One example is the BMC you know, the best master clock algorithm. It talks about using the best clock, but you know, the famous example is if you got a clock in New York and a clock in London, you have to use the best one if you're going strict PTP. Even if you're going across the Atlantic Ocean over you know, a pretty sketchy MPLS link, and you're going to have so much network inaccuracy. So,
Yeah,
you know, there's a lot of things.
Sorry, go ahead, Hank.
Sorry. Go ahead.
I was just going to say, yeah, that's if you go with the default, but you know, of course, there's priorities which can override that and administrative. But yeah, I think that the point you were making, where you take advantage of the PTP where it exists, and especially the bridges, the switches, I think that's a key piece. 1588 took the approach of letting 1,000 flowers bloom with all of these profiles. One of the challenges will be to consolidate, I think, all of these profiles, because or somehow have some better way of switches supporting many or all of them without a huge software burden. But I think that's one of the challenges.
My gut tells me you're going to have a specific profile for each use case, and watch it with the switches. Some of them have very good transparent clocks. Some have good, you know, boundary clocks. But I used to work for a different company selling a PTP-based client. The thing is, some switches are good, some are bad. You have to measure, and I think that's probably the one big thing I'll give you is don't trust anything. Measure it. You know, you have to measure and see how good are your switches performing. And
yeah, one of the observations
on
this aspect that we observe is that if you do not have a P2P aware switches, the PDV values goes to 180 nanoseconds per hop. And end of the day, when you put multiple switches in there, I mean, let's say two switches in there, P2P unaware switches, you are going to have around 7 microseconds of clock drift. And given the conditions and everything else in the network, it becomes pretty troublesome. More switches you connect in a series.
What we found when I was with that other company is that, again, our customers mostly had low latency switches, you know, high-end switches. So there wasn't a whole lot of jitter. There weren't very deep buffers. And going from the grandmaster to the client, our customers could get, you know, usually under a few hundred nanoseconds accuracy from the client to the clock. Again, it depends on which switch you're using, because if you're using like my personal home router, you're not going to get that. But if you're using like a high-end Cisco or a Arista or something like that, you know, we found that some of those actually work better when you turn the clock off.
Yeah, testing methodologies for sure. I think Anand, you're running that group, aren't you? Right, that defining those methodologies, that is critical, because yeah, unless you test it, you don't know that it's true.
I agree, Kevin. We've defined it well for telecoms profiles and use cases, that we need to expand beyond that. And yeah, that's what the work's about.
Yeah.
Okay.
Great.
I would like to forward here just to show you our wiki page is updated with today's sessions. The videos will go there as well. And in general,
Hey, Elad, are you sharing your screen? Just out of curiosity.
I thought I was.
I think you.
We don't see it, so that's why.
Try again. Okay, so that's our wiki page, guys. And all of the information to get started or to join is there, whether it's the work streams and the leaders, our regular biweekly calls as they go on. And we also have the links to the Tech Talks today uploaded. So that's how, very simple to engage with us.
Also, I'd like to thank Archana and Kali for all this amazing work. Like, definitely without them, this was not going to be possible.
Well, a couple of other things as we're departing. First of all, the summit, OCP Summit is coming up in October. It's a month early this year, so it will be occurring October 18th, 19th, and 20th in San Jose, California. It will be in person. There will be no virtual aspect to it. We're expecting pretty much everyone now that's traveling to be here. It is 3 days this year, which is very different from last year. So we have a little bit more breathing room, but it also allows us to have a little bit more time to talk and present. So the call for papers for TAP is available now. We're looking for abstracts between now and the end of the month. I know it's coming up really quickly. And that also includes any kind of demos that you might want to do at the Experience Center. I know last year it was a huge success in terms of the demos that you did there. So something to think about between now and the end of the month is that we do have that. And then the third thing is, I know we're looking at future technologies as well. And there's a lot of really good work that's going on here and possibly in academia and around some of the research facilities around time and synchronization. And so our Future Technology Symposium is also going on. Normally it's on day 0, but this time around it's actually on day 2. And that allows a little bit better cross-pollination of both our communities, right? The things that people are looking at 3 to 5 years from now and the things that are being worked on today in our project communities and the things that you're working on. So that call for papers is slightly different than the abstracts that we're looking for at Summit. This is a little bit more of a formal paper that academics and grad students and PhD students do. Last year, there was a $10,000 award for the best paper, and it was won by Cloud and Heat. Many, many thanks to Meta for sponsoring that. But this year around, we're expecting the exact same thing. And we're really looking for a lot of energy and response from the community. So this is your opportunity, TAP community, to come forward, bring your ideas, bring concepts that you think would be very relevant. We're very excited to do this in person again. I know last year it was one of the first events in the Bay Area, so hoping to carry on that tradition, and wanted to leave you all with that parting thought. I've also posted the link in the chat for where you can find the video and the chat transcript and the slide decks from today, along with the wiki that Elad posted. This will also be on the OCP past events page, and between Kaylee, Kate, and myself, we'll do our best. All the slides are locked and loaded, but the video is still processing, and we'll get to that hopefully by the end of the day, if not first thing tomorrow. So spread the word for those that missed today, because again, the more we have on the community, the better off we are. And it helps offload a lot of work for Elad and Ahmed when the community is doing, most of the work. But many, many thanks to the organizers here. They've spent hours curating the content, and to all the speakers that have come forward and shared their ideas with the community. So thank you so much from OCP, and we're very, very happy that you can make it today.